A wormhole, or Einstein-Rosen bridge, is a valid solution of Einstein's field equations for general relativity that connects two regions of space that otherwise could be very distant from one another or even in different universes. The visual representation of the wormhole's space-time curvature as back-to-back funnels resembles connecting the singularities of two black holes, but it has nothing to do with black holes. There is no infinite density singularity of mass energy in a wormhole. Actually, there may be no mass at all inside the wormhole, producing the curvature of spacetime. This is a spacetime curvature solution without a point mass to produce the curvature. Wormholes are a very useful device in science fiction to bypass traveling otherwise long distances in galaxies or the universe. But can they exist? Wormholes have not been detected by astronomers. Wormholes may exist, may not exist at all, or might only exist at the infinitesimal Planck length scale, where quantum gravity would be required to unify general relativity and quantum field theory, and spacetime may be like a rapidly changing foam. Physicists believe there is no way to create a macroscopic wormhole using the ordinary matter and energy of our universe, even if you could use an infinite amount. In 1988, it was proposed that a spherical shell of exotic matter with negative mass energy could hold a wormhole open, but this is highly speculative, and physicists know of no negative mass energy in our macroscopic universe. If a wormhole exists, light and gravitational waves could pass through the wormhole in both directions. Some articles propose that matter might be able to traverse a macroscopic wormhole, though the radiation might be intense and perhaps fatal to organisms. Other articles propose that a single particle of ordinary matter traversing a wormhole would destabilize the wormhole, either resulting in a pair of black holes and singularities or evaporating into a huge release of energy, as the spacetime curvature returned to flatness on both sides. In 2021, physicists proposed that it might be possible to create a microscopic wormhole using ordinary matter of positive energy from our universe, and that electrons could potentially traverse the wormhole. I believe the particles required to create this wormhole are hypothetical and speculative at this time. It is sometimes stated that a wormhole may allow someone to time travel to the distant past. I believe this is overstated, but you may want to read about closed time-like curves. If we had a verified theory of quantum gravity, physicists would be able to understand what is and is not possible with wormholes. Dark matter. In this course, we will not cover dark matter as the plausible cause of the non-Keplerian galactic rotation curves. However, in terms of general relativity, any dark matter is just matter. Like ordinary visible baryonic matter, dark matter's mass curves spacetime, and curved spacetime tells all matter, including dark matter, how to move. Like ordinary visible matter, if a dark matter particle crosses the event horizon, it will never escape a non-rotating black hole. Please do not think that dark matter particles, if they exist, pass through the black hole because they do not interact with ordinary matter. That's not true. The gravitational lensing produced by galaxies and galaxy clusters is principally due to the dark matter that dominates the mass of the galaxies. Antigravity and dark energy. There is no known antigravity at scales of galaxies or smaller. Sorry, no antigrav hoverboards and hover cars, but there is magnetic levitation. On the cosmological scale, dark energy seems to be a constant energy density present everywhere, including especially the hard vacuum of the cosmological voids between galaxy superclusters. The dark energy density remains constant as the universe expands over time, which increases the total energy of the universe over time, which accelerates the expansion of the universe over time. So this is loosely like cosmological antigravity in that it expands the space between galaxy superclusters over time. Physicists do not know the origin and mechanism of dark energy. Perhaps it is an inexplicable cosmological constant of general relativity, or perhaps some residue of quantum field theory energy of the vacuum ground state. An article in February 2023 speculated that cosmological dark energy might be the effect of very long-distance coupling between black holes' singularities across cosmological distances. It is unknown whether the nature of dark energy will be discovered in coming decades, or it will remain a cosmological parameter without further explanation. Light, Part 1. Radial, for non-rotating black holes. Light paths, called world lines, passing near to or into a black hole's event horizon, are very complicated, and even more complicated is the direction an observer should look to see light from a given star behind the black hole, which is a function of the observer's position and motion. In this section, we will look at the simplest, yet still complicated, special case of light traveling radially inward, incoming to, or radially outward, outgoing from, a non-rotating black hole, after we cover ordinary flat spacetime, no gravitating mass. This section is of particular interest to light crossing the event horizon and to plunging observers. If this section does not hold your attention, skip to the next section. In special relativity and general relativity, time does not pass for light world lines. A light ray's wristwatch time never changes. Its d tau equals 0. Using this with the metric produces the light world lines. We want to know about radial world lines near and inside the event horizon. For this, there is a better metric than the Schwarzschild metric. We won't do the math. We'll look at the result. This graphic shows the world lines of light emitted from the observer at the center in all directions, far from any masses, flat spacetime. The future light cone represents all light world lines emitted from the observer's position and time. The vertical axis is time. The horizontal axes are any two of the three spatial dimensions. Isotropic light travels outward in all three spatial dimensions, but we can't easily represent a four-dimensional image of different spherical shells at different times. Nevertheless, it is called a light cone, not a hypercone. The scaling, or units, of the space axes is light seconds, such that the slope of the light cone is 45 degrees. The observer can move in space, but can only travel at speeds less than the speed of light in vacuum. There is no faster than light warp drive. So the observer's entire future lies within the future light cone. The observer's entire past lies within the past light cone. Here is a simpler diagram showing a single spatial dimension. The observer is at the center and has emitted the upward light rays. This light ray moving to the right, this light ray moving to the left. The observer's future is upward toward increasing time, within the future light cone, shown in yellow. This is for flat spacetime, no masses. An event here, in the past, could have influenced this observer's past and therefore influenced its present and future. However, an event outside the past light cone, here, could not have influenced this observer's past or present, but can later influence the observer's future. Here. Now let's look at how light behaves when emitted radially inward, ingoing, or radially outward, outgoing, near and within a non-rotating black hole's event horizon. The gravitating mass is at the left, here, the singularity. Far to the right, far away from the mass, spacetime would be nearly flat, and the future light cone has plus and minus 45-degree lines. As we move left, closer to the event horizon, the future light cone, here, has rotated counterclockwise toward the black hole and has narrowed due to the curvature of spacetime due to the mass. So this angle will be less than 90 now, and this angle will be more than 90. Let's look at the rightmost light emission from outside the event horizon. The arrow to the upper left is light emitted radially inward, incoming at the speed of light. The arrow to the upper right is light emitted radially outward, outgoing at the speed of light. Here we are only looking close to the emission. Space is curved near the black hole, so don't be misled into thinking that the slope, dr dt, is the speed of propagation. It isn't. The tilting of the light cone tells us that there is time dilation and gravitational redshift here versus distant flat spacetime. The curvature of spacetime for the black hole makes it very confusing to present or understand how light can always travel at the speed of light relative to space, and yet is also seemingly not traveling at that speed relative to space. Here's an imperfect analogy. Consider an escalator moving downward toward the black hole. It's easy to walk down the down escalator at a fixed speed relative to the escalator. It is hard to walk up the down escalator. We don't make any absolute progress. If the escalator is fast, we can't do it. We still go down. The analogy is imperfect because space is not moving toward the singularity, but it is highly curved toward the singularity, and it's hard to get a satisfying feel for curvature. So remember the down escalator analogy. Here is the light pulse emitted at the event horizon. Here's the event horizon. Its quote outgoing unquote radial light ray is straight up. This outgoing light is forever parked at the event horizon, at one point in space, as if trying to move to the right, but never making any progress. And yet, the observer who emitted it sees it as moving outward at the speed of light, because they are moving inward and spacetime is strongly curved. Note that this is still radial light, not the tangentially orbiting light case of the ring of fire at 3/2 Schwarzschild radii. Inside the event horizon, such as here, every quote outgoing unquote light ray is actually moving inward and will fall into the singularity. Observers outside the event horizon never see light emitted at or inside the event horizon. Inside the event horizon, the light cones have rotated such that the future always points to the left, toward the singularity. The entire future is here, and it points to the left. In the Schwarzschild metric, this occurs because the coefficients of the faraway time, dt, this coefficient, and radial coordinate, dr, this coefficient, change sign when we go from outside to inside the event horizon. This term is positive outside the event horizon and negative inside the event horizon. Loosely speaking, time is behaving like space, and space is behaving like time. The march of time has become descent into the singularity and then oblivion. However, here we really should use a better metric that is not infinite at the event horizon, which we won't cover. Let's look at a plunging observer sending light pulses radially inward and outward. This is the path of the plunging observer. These are light world lines. So when the plunging and the event horizon is here, so when the plunging observer is at A, he emits a light pulse inward and a light pulse outward. And the light pulse inward does go inward and eventually hits the singularity. The light pulse outward does go outward and it escapes the black hole system. Here we see that light world lines on this diagram curve after emission. Outgoing light world lines curve away from the black hole, outside the event horizon, and curve toward the singularity inside the event horizon. The vertical axis is time, so this is not a curving path in space. It is changing coordinate velocity in space and time, but still traveling at the speed of light according to all observers. When the outgoing light emitted outside the event horizon finally reaches far from the mass, it will eventually look like a 45-degree line for flat spacetime. Now, suppose two spaceships plunge into the black hole, one behind the other. Will the second ship see the first ship's rear running lights or see blackness? I'm going to draw a second spaceship's plunging trajectory. I'm going to start at the singularity and go out only because that way I can draw a little better, but so this is the trajectory of the first spaceship, and the red trajectory is the second spaceship, which is slightly behind it. They have the same plunging profile, it's just that the second spaceship is a little behind. Now, for the interval I've drawn, the second ship will see the outgoing pulses that the first ship sends at point A. It was emitted here and it will be seen here. It will see the light pulse emitted at B. The red spaceship will see it here. The light pulse emitted at C, the red spaceship will see here. The light pulse at D is parked at the event horizon, but the red spaceship will see it here. The light pulse emitted at E the red spaceship will see it here, but the light pulse emitted at F has already hit the singularity and will never be detected by the red spaceship. If the red spaceship were further behind, it would not see the flash at E. It will always see the flash at the event horizon, as the second spaceship crosses the event horizon. The first ship might see some of the incoming flashes from the second ship sent inside the event horizon if the ships are close enough together. I believe the first ship will see these flashes as redshifted due to its speed, though I'm not sure. Both ships could see starlight from far away behind them, emitted long ago, and could receive communications previously sent from outside the event horizon for part of their remaining time. I believe the ships will see this light as redshifted due to their speed, despite the strong gravitational blue shift of the inbound light, though I'm not sure. The black hole in front of them will look black, but they might see plunging hot gas or other plunging objects in front of them being spaghettified in a flash. There is a 3-page write-up of what a plunging observer would see inside the event horizon of a billion solar mass black hole plunging for 1.8 hours. That link is available in the lecture script PDF. In that document, the mass of the black hole is also used as a distance and time. It is half the Schwarzschild radius. The black disk we see at any time is not a solid, not material. It is the volume of space, spacetime, from which light never reaches our present point in spacetime. Light trajectories for non-rotating black holes. Light always travels straight, locally, in spacetime. In flat spacetime, light travels in globally straight lines. In curved spacetime, traveling straight locally at each point produces a curved trajectory in space called the geodesic. Trajectories curve in the direction of the mass that is curving spacetime. It is not that light has mass and its mass is attracted to the central mass by gravitational force. Light is massless and travels straight locally in spacetime, whether spacetime is flat or curved. The aging of a light flash along its world line is always zero. Aging d tau equals 0 along every differential increment of the light flash world line. We can use this with the Schwarzschild metric or a different valid metric to determine the light trajectories. However, we will just look at some results for a non-rotating black hole. The curvature of spacetime affects all electromagnetic radiation equally, and also gravitational waves. I will use the term light, but radio waves to gamma waves all curve identically. This is not a function of photon energy. As shown in the left diagram, non-radial light will curve its trajectory toward the black hole. If the original trajectory is close to the radial axis, so here's the radial axis, and this light wave is coming in kind of close to the radial axis. Light will plunge into the event horizon here, and then into the singularity. An observer to the left of this black hole would not see that light beam. In the second picture, the trajectory is a little further from the radial axis, and this trajectory circles the black hole and then spirals into the event horizon and then into the singularity. If we were an observer to the left, we would see a black hole shadow inside 2.6 Schwarzschild radii, so light from here to about here, light emitted that way, that way. In this region, we're going to see a black circular disk, the black hole shadow. Light from background stars does not reach us in these direct trajectories. More on this later. But if the original trajectory is a little further yet from the radial axis, as in the third picture, light can orbit around the black hole one or more times before escaping to infinity in some direction. The case of the ring of fire is in between the second and third pictures. A distant observer would see the ring of fire bordering the black hole shadow at 2.6 Schwarzschild radii, though the ring of fire is located at 1.5 Schwarzschild radii due to the curvature of light trajectories. In the bottom left image, light was deflected and escaped without orbiting. For an observer looking in the direction of the black hole, we might reasonably assume that we cannot see the stars behind the black hole, that their light is blocked by the black hole event horizon in front of us or by the black hole shadow. But actually, at any location outside a black hole shadow, the observer can see the stars behind the black hole, as their light trajectories are curved by the strongly curved spacetime. However, the star will appear in an unexpected apparent location. More than this, there will be multiple images of each star in the galaxy at various locations along the ring of fire edge of the black hole shadow. The diagram on the right shows that an observer here, located at 4 Schwarzschild radii from the black hole, that observer will see light from one distant star. The distant star is at the upper right. The distant star is over there, and so we see its light curving toward the black hole. So we perceive that the star is in this direction because of the curved light. we also see it we also see two other images of it. Some of that light comes a little closer to the black hole and goes around the black hole, and we perceive that light as coming. I didn't draw it very well, but we perceive that light as coming from that direction. And some more of the light from the star comes this way, around the black hole, and we think that the star is in that direction. So we see three images of the star in three different directions. We see an image apparently coming from the red direction, an image apparently coming from the green direction, and an image apparently coming from the blue direction. Now, the ring of fire is going to appear to be something like this, appear to this observer. The ring of fire is going to appear there. It's going to appear larger than we would calculate for the ring of fire because of curvature of space. Within that ring of fire, this observer is going to just see black hole shadow. Light is doing stuff in there, but this observer doesn't see that. The inner edge of the accretion disk at the ISCO will also appear wider than expected, but will appear close to the ring of fire because curvature is stronger near the ring of fire than at the ISCO for a non-rotating black hole. Some of the multiple images of each star will be bright and others dim. Some will be spread into an arc. Many images will be indistinguishable from one another, being part of a band of white light. Analyzing light near a black hole is complicated. Light trajectories get curved by the curvature of spacetime due to the gravitating mass. Given a trajectory of light from a given star, we would have to calculate which direction an observer needs to look to see that light, as the observer's motion results in aberration of the light path. Then we need to calculate whether the light along that path will be blue shifted or red shifted for that observer. Then we need to calculate whether that light will be focused and intensified or will be dim. This requires a lot of numerical calculation. In this simulation of a non-rotating black hole, without an accretion disk, each star image is doubled on opposite sides of the black hole. This red star and this red star are the same. This white star and this white star are the same. The image that is further out is the primary image, and it can be brighter than the star would be without the gravitational lensing of the black hole. The closer in one is the secondary image, secondary ghost image, and it's dimmer than the primary image. There could also be additional ghost images in closer alternating sides, dimmer yet, including right near the ring of fire. This is a simulation of orbiting a non-rotating black hole with no accretion disk at 20% of the speed of light. We see two images of each star on opposite sides of the black hole. It's an interesting, complicated, beautiful, mesmerizing pattern. Let's watch a specific background star. Let's watch this star appearing to go there, and this is the same, going in opposite directions. If we look at the top half of the image, stars are moving left to right as we orbit the black hole. But inside this Einstein ring, stars are moving right to left, apparently moving. Our image is moving. And there's another inner Einstein ring where the stars are moving left to right again. That star there. This is a NASA simulated view of a thin accretion disk feeding a non-rotating black hole with no jet. The accretion disk is shown in brown, orange, red, orange, and a little yellow. I believe a real accretion disk would be much hotter and would look bright blue-white in the visible spectrum. The black hole shadow is circular for a non-rotating or slowly rotating black hole. This is the ring of fire. The ring of fire and the accretion disk are in the equatorial plane, nearly edge on to our view. So this is light coming toward us without being bent very much. But the accretion disk looks vertical due to the gravitational lensing of light above and below the black hole. So the light from this arc here is the ring of fire behind the black hole, has emitted some light vertically upward, and it got bent over the top of the black hole and is coming toward us. And this is the ring of fire behind the black hole that emitted some light vertically downward, and that got bent toward us under the black hole. The black hole shadow inside the ring of fire, it appears larger than the calculated value, and the distance between the ring of fire and the accretion disk is smaller, so this distance is smaller than calculated due to the strong curvature of spacetime bending the light trajectories. This accretion disk is oriented nearly edge-on to us and rotating left to right in the foreground. With the bending of light, we see the portion of the accretion disk that is behind the black hole, both the top face and the bottom face. For the top face of the portion of the accretion disk behind the black hole, we're seeing light that was emitted upward and curved over the top of the black hole and toward us. Similarly for the bottom face, light emitted downward and it curved underneath the bottom of the black hole. Exactly what we see depends on our viewing angle and also our motion, so it's complicated. Again, I believe this accretion disk would look blue-white, but it is shown as orange. This simulation from the development of the movie Interstellar is of a rotating supermassive black hole with no accretion disk. Notice that the black hole shadow does not appear as a circle here. It is scrunched on the left and pushed out on the right. The rotation axis would be vertical here, and the rotation would be left to right in the foreground. So the black hole shadow is distorted, not circular, and the trajectories of all the stars are severely distorted. This simulation from the development of the movie Interstellar is of a moderately rotating supermassive black hole with an accretion disk nearly edge-on to us. We see the ring of fire here, and it looks pretty circular, so this black hole is not rotating very fast. As this black hole is rotating slightly, I believe the ring of fire is actually a shell of fire in or near the equatorial plane, mostly edge-on to our view. It looks vertical due to the gravitational lensing. So what we're seeing here is actually behind the black hole, and what we're seeing here is behind the black hole. I believe the shell of fire would look much different for a rapidly rotating black hole, as Gargantua is supposed to be in the movie, perhaps only appearing as a point on the left. This image looks hazy, gray where we expect black. This is an intentional simulation of camera lens flare. It is meant to give the impression of how painfully bright the white areas are. It is not that the black hole shadow is emitting gray light. So the accretion disk goes from here all the way to here. It's near the edge onto us. It is whiter as we get closer to the black hole, where the energy of the accretion disk particles gets very high for a rotating black hole. So the energy goes up, the temperature goes up, the radiated light appears whitish or blue-white. Here's the accretion disk. But all of this accretion disk back here is actually behind the black hole, and we're seeing the top surface of it. And the accretion disk here is actually behind the black hole, and we're seeing the bottom surface, and all of its light is bent toward us by the black hole. Now, this disk is presumably rotating in this direction. Not represented here, the Doppler shift of the motion of the accretion disk and frame dragging would make the visible light, a little brighter here, where the light is moving toward us, and a little dimmer here, where the light is moving away from us, but it would still be blue-white. This black hole simulation is only rotating slowly, not rotating near the maximum rotation value that would be required to generate the time dilation that the movie required. The extreme appearance for the maximum rotation was deemed to be too confusing and unfamiliar for the film. In the movie, Miller's planet would be, at the ring of fire. But for the more extremely deformed case of maximum rotation that we're not seeing here. A jet is not shown here, as this accretion disk has been posited to not feed much mass to the supermassive black hole. This is a simulation of plunging into a non-rotating black hole past its event horizon. Notice how the black hole shadow increases in size and fills our forward view. Also, notice that we cannot easily tell when we've crossed the event horizon. The view changes smoothly. This is all we will cover about how light behaves. Artificial gravity. Sorry, there is no artificial gravity deck plating for your starship. Use rotation, centrifugal force, or magnetic boots. Warp drive and faster than light travel. Sorry, warp drive for your starship and faster than light travel or communication or subspace are still science fiction at this time. However, the Alcubierre drive is interesting as a theoretical possibility for the future for a warp bubble. You can read more about it on Wikipedia. However, the ship would have zero speed relative to the space inside the warp bubble, so would not be going faster than the speed of light relative to local space. The space-time warp bubble would go faster than the speed of light relative to space outside the warp bubble, and supposedly this is permitted by general relativity. However, nothing inside such a warp bubble could affect the bubble. the spaceship could not start or stop the bubble or change its direction or speed. In vacuum, light travels at the universal speed of light relative to local space, and matter travels at less than the vacuum light speed. However, 2 points of space can move away from one another at faster than the speed of light. This is allowed in general relativity, and it occurs in an expanding universe of homogeneous isotropic mass density, and it occurs in our universe. Almost all of the space created by our Big Bang is moving away from our region of space at faster than the speed of light and is no longer observable by us. Our observable universe is the region of space whose recession from us is less than the speed of light, everything that we can still see. We will not cover expansion of the universe in this course, though it's a course that I want to create in about a year. Relative to local space, matter always moves at less than the speed of light in vacuum. However, the speed of light in materials, for example air or water, is always less than its speed in vacuum. Matter can move at speeds higher than the speed of light in air or water, while still less than the speed of light in vacuum. When this occurs, such as for cosmic rays and neutrons emitted by underwater nuclear reactors, a pale blue light called Cherenkov radiation gets emitted. Here is material that we are not covering in this class, but you can get more information from Wikipedia. Tidal locking and tidal heating, gravitational slingshot, gravity assist, black holes with electrical charge, the no-hair theorem, holographic information storage at the event horizon, black hole temperature and entropy, quantum gravity, gravitons, what would happen if a small primordial black hole hit the Earth, time travel to the past via a wormhole, closed time-like curves, galactic rotation curves and dark matter, expansion of the universe and the Big Bang, also Roche-Lobe overflow, and magnetic reconnection in supermassive black hole jets. This is the end of the course, Gravitation and Black Holes, and thank you for joining.